Hello everyone, welcome back. Today we are going to look at some of the turbulence models which are based on Bugenus hypothesis. As we saw in the last class that we have this unknown Reynolds stress tensor, okay, and then we can there are 6 stresses and we can use the Bugenus hypothesis and we can reduce the number of unknowns to one unknown, which is the eddy viscosity. That means your stress is related to the mean flow gradient with this proportionality constant as the eddy viscosity or the turbulent viscosity. Okay. And today we are going to look at how to model that viscosity part, okay, the eddy viscosity. As we have been discussing, it is not a property of the fluid, it is a property of the flow. So, it has to be determined from the flow somehow. Okay. And we looked at earlier that we are looking for two scales, okay, for the viscosity. One is the velocity scale and another length scale. This is your kinematic eddy viscosity nu_t, which is meter square per second, okay, and then you have the velocity which is meter per second, and we have the length scale which is meter. So, that will give you the meter square per second. So, before we go to the more advanced model like K epsilon, K omega, SST omega, etc., I want to look at some of the earliest development of these turbulence models. So, one of the earliest model which was proposed by Prandtl, it is called the Prandtl mixing length model, and it has worked quite well for very simple flows, canonical flows, and that is why it is important to know about the historical aspect of this model development. So, what he proposed, he actually borrowed the idea, Prandtl borrowed the idea from the kinetic theory of gases. And as you know that in the kinetic theory of gases, you have these molecules and you define a mean free path called lambda. So, mean free path is the distance which a particle travels or a molecule travels before it hits another particle, right. So, that is the mean free path. Okay. So, using the same idea, Prandtl proposed a length called the mixing length, right, LM. Okay. So, as we said that the eddies are of different sizes. So, prescribing one single length scale is not an easy task, right, but we can borrow the idea of Prandtl. I mean what he assumed, that can we think of, let us say we have two layers here, okay, there is one layer here and one layer here, okay, and molecule, as you know that between these two layers the molecule keep on jumping, right, they can jump from here to there or from the top to bottom, right. So, his idea was that can we think of a length where the molecules jump while keeping the momentum conserved, right, and that length he is told as the mixing length, which is denoted here by LM, right. So, that means that LM is the length at which basically one molecule from one layer jump to another layer separated by distance LM, okay, such that it does not lose its momentum. That means the eddy basically does not get mixed everywhere, right. So, that length is broadly called as the mixing length. Okay. So, as you can see that that is the definition of the mixing length, and we will see that how do we see it for different kind of flows. Okay. The other length scale that you want, or the other scale that you want, is the velocity scale, right. So, the way he defined the velocity scale is basically within that length the flow is basically governed by some kind of gradient, right. So, if you make an eddy, okay, so this is, let us say this is your eddy, okay. So, this is how the eddy looks like, right, it is a picture of the eddy, right. So, if you cut it here, okay, so you have something going on the right hand side, okay, and something going on the left hand side, right. So, this is a picture of an eddy, right. So, let me create it here. So, this is how the picture of eddy looks like, right. So, his argument was that instead of talking about a velocity, we can talk about the velocity difference, which is the delta u here, right. So, if you can find out the velocity difference across this layer, which is LM, okay, mixing length, then we can specify the velocity. So, what is the best way to specify this delta u? So, he said that okay, if you know the gradient del u by del y, okay, you multiply this by LM, okay. So, that will give you the velocity scale, okay, that is your delta u, not grad u, So, this length scale, this velocity scale can be used for the prescription of the velocity. So, now we got the Lm also and u0 also. So, using these two things, and of course, a better way to prescribe it is the putting this del u by del y. You can take the absolute value of that instead of taking the just del u bar by del y, and the reason for that is as we have been discussing that the eddy viscosity, the mu t that you are talking about has to be positive, right. Recall the diagram where we talked about rho u prime v prime, and we said that the rho minus rho u prime v prime has to be positive, right. So, because if the u prime increases, v prime decreases, and if the u prime decreases, v prime increases, and vice versa. So, this entire quantity is positive. So, in order to have that property here also, so we can separate it as L m del u by del y, and then you multiply it by del u by del y, right. So, your turbulent stress or the Reynolds stress, okay, will be basically mu t del u bar by del y, right, and mu t is further basically u0 L m del u bar by del y, right, and u0 is nothing but L m del u bar by del y, okay, absolute into L m, okay, multiply by del u bar by del y, and finally, this becomes equal to L m square del u bar by del y multiply by del u bar by del y. Okay. So, this quantity, as you see, this is a positive quantity, right, and your stress will depend on the direction of the velocity gradient, which is what we have been talking about, that it depends on the mean flow velocity gradient, right. So, and this quantity that you have got here, this mu t, is basically a positive quantity, right, and of course, I think you have to basically multiply by rho here, because this is mu t, that is rho nu t. So, this will be rho here, okay. So, rho L m square del u by del y del y. Okay. So, now the question is, how do you get this length scale L m? Okay, we have got the idea that we want a mixing length, okay, but what is its value in a particular flow, right. So, again what argument Prandtl gave, and he himself was not very convinced of this model. Okay. So, let us understand this, that he proposed it, and because there was no model anywhere time. So, he proposed this, but he himself was not very convinced of this model, and he said that it might not work for the complex flows, but indeed I mean it worked for very simple flows and it did not work for complex flows, but it gave basically so many ideas that that led to development of more complex models, right. So, how do you basically prescribe the mixing length? So, there his argument was, let us say you have a wall here, okay, and how the eddy is dictated? It is dictated by the distance from the wall. So, let us say if you are talking about here, okay, so your eddy size will be like this, right, and let us say that if you are talking about let us say this is your y axis, make a y axis also, okay, and let us say if you go a little bit above here, okay, so then it will go, the eddy size will be like this, okay, and if you talk about this distance as y, so this is my y and this is x. So, his argument was that this length scale is somehow a function of y, right. And then he again made the argument that in the log law region your velocity gradient is related to this u tau by k kappa y that we have seen, and by having this argument that the total stress is a constant stress layer. So, at the very beginning it is the viscous stress, then it is the buffer zone, and then you have the logarithmic zone, but in all these layers the stress remains constant. So, you have the viscous stress which goes down like this is very high. So, this is my y, okay, and the other stress which is Reynolds stress goes like this. So, your viscous stress decreases, okay. So, this is my distance, okay, let me call this y, okay, this is very close to the wall 0, and this let us say let us call it y plus, okay, and this is around maybe 30 or 100, okay. So, initially you can see that this is my viscous stress and this is my Reynolds stress or Power stress, okay. So, the summation of that, if you sum that up everywhere, okay, so that remains constant. So, basically the viscous stress is going down and the Reynolds is going up as you go away from the wall. So, the total stress can be taken as the stress near the wall, which is rho u tau square, and which is given as rho Lm square u tau square by Ky, and if you compare this, that will give you the value of length scale as kappa y. The length scale of kappa y comes from this argument that my length scale should be proportional to the AD size, which is the distance which is from the wall. So, there has to be a proportionality constant. So, Lm is proportional to y, and that becomes Lm equal to kappa y. This is same kappa that we have seen earlier, okay, in the log law region, and this kappa can be used here in Lm square, okay, and finally you can basically get this model, which is the Prandtl mixing length model. Replace this Lm square by kappa y and you get this. Okay. So, this is the Prandtl mixing length model. Now, when Van Rist came, he suggested that this model cannot be valid all the way to the wall. The reason for that is near the wall, very close to the wall, the turbulent stress is very small, okay, especially in the viscous sublayer. Okay. So, that means that there is a damping that occurs very close to the wall. Okay. We need to incorporate that damping, otherwise the model will not be valid very close to the wall. Okay. So, the mixing length basically which indicates how the mixing takes place due to the AD, it has to be damped close to the wall because of the presence of the viscous sublayer, where the turbulent stress is very small. Okay. So, what he proposed that you can change the definition of mixing length. So, not only the kappa y, you multiply with this quantity 1 minus exponential minus y plus to the power by a plus, and you can take this a plus value as 25, which is suggested by Van Rist. Okay. So, this basically provides the essential damping that is necessary for the model to work very close to the wall. Okay. So, you can see here in the diagram. Okay. So, this is the diagram of basically Lm equal to Ky, okay, this is equal Lm equal to kappa y, okay, and what is the diagram of Van Rist is basically let me use another color. This is the diagram by Van Rist. Okay. What it does is basically it follows the profile not only in the log law region, but also in the viscous region. It is very close to the Spalding's model that we have talked about. That Spalding's law basically unifies the law of the wall, which is log law, as well as the region where u plus equal to y plus, right. So, using that kind of argument, Van Rist proposed a model modification length scale, where the model works very close to the wall also in the viscous sublayer also, right. And then we had some more models. These are all zero equation model. Why it is zero equation model? Because you are not solving any equation. For the length scale, we are using the geometry, because it is coming from the y, the distance from the wall. Okay. And for the velocity scale, we are making an argument about the velocity gradient present between two layers which are separated by a mixing length. Okay. And that is given by the velocity gradient multiplied by that mixing length. So, what Cebeci-Smith said that maybe it is a better idea to get the minimum value of kappa y and something from the boundary layer value, right. So, if you have a shear layer like this, okay, so you have this gradient coming, this is kappa y, and let us say this is your boundary layer thickness, which is delta. Okay. So, then you can take a measure from the kappa y as well as the delta, which is 9% of the delta, and take which one is the minimum, and you can take that for making the getting the AD viscosity. So, this is the model which is proposed by Cebeci-Smith, and it has shown some improvement over the Prandtl's mixing length model. Okay. Now, for mixing length model, I mean, if it is there is a wall, then it is fine, right. What if there is no wall? Let us say there are free shear flows, like which is shown here, right. So, in the wall bounded flow, Lm is related to the distance from the wall, right, as we have seen there, and you can see that if you would have gone only through the Prandtl mixing length, then this will kappa y will keep on increasing, right. But if you use this argument of the Cebeci-Smith, then it will get limited here. Okay. So, this will be minimum of either kappa y or 0.09 lambda. Okay. So, this you get the mixing limited, or it should not arbitrarily increase when you go away from the wall. Okay. For the free shear flows, the argument was instead of having the boundary layer which is not there in the free shear flow, you can have some kind of width. Okay. So, for example, you have the jet width which is given by delta, or in the mixing layer, or you have the wake, right. So, you have this widths present. So, you can take some fraction of that width. So, they have used this for example, mixing layer 0.071. All these numbers that you see here like 0.09, 0.071 are from the experimental observation. So, it is kind of data fit. Okay. You try with different numbers. Okay. Of course, you have some argument, you know that it has to be lower than the boundary layer thickness or the wake width, but how much lower it should be, right. So, you use different values, okay, and then try run the simulation, compare with experimental data, and the value which matches the best is the value that you are looking for. Okay. So, for the plane jet is around 9.8% of the jet width, or 8% for the round jet, and also for wake it is the higher value which is around 18%, right, and these numbers worked well based on their experience. Okay. So, for simple flows it works fine. Okay. It is very simple to implement this mixing length model, whether it is Van Rist or Prandtl or Cebeci-Smith, and there are some more models also, right. So, the advantage of that is these models is that there is no additional equation, you are not solving any other dynamical equation like you do in the K epsilon or K omega, right. We will see those models very soon. Very simple to implement, just some algebraic equations, and it works for well for simple shear flows. Okay. But you will see that it has got several limitations. For example, this LM is geometry dependent, right, and if the geometry is very complex, recall what we were discussing in the last class, like let us say you have a geometry like this and you want to find a uniform length scale, it is changing everywhere, right. So, for this kind of simulation, if you put one length scale which is not changing with space, okay, you are going to get wrong values of that parameter, right. So, it has to be dynamic, okay, and it should relate to the local turbulence properties. Sometimes the flow may be highly turbulent based on local Reynolds number, it may be laminar or it may be transitional also. So, it should relate to the local turbulence properties, right. So, that is what led to the development of more complex models. We saw some models about one equation model, two equation model. So, I do not have time to go through each and every model, but I will take you through some most popular models. Okay. So, let us start with the K epsilon model. Okay. So, before we start, note that K epsilon model is not a single model. Okay. It is a class of models, okay, where the equations may be different, the parameters may be different, the coefficients may be different, right. So, and also the philosophies are also different. For example, in realizable you have a different philosophy how you treat close to the wall compared to let us say standard K epsilon model or RNG K epsilon model, right. So, there are so many K epsilon model, I mean a few are like standard K epsilon which is popular, okay, and then you have RNG, okay, and then you have realizable, okay, and then these are basically the eddy viscosity model. Then you have this cubic K epsilon also, okay, but this is not just eddy viscosity, this is a non-linear eddy viscosity model. Okay. So, here the viscosity not only depends I mean not only linearly dependent on the velocity gradient, but it may also depend quadratically or even higher powers of the velocity gradient. Okay. So, in all of these models like it is K epsilon or K omega or SST K omega, even some more models, the basic transport equation that you get is the kinetic energy equation. And why do you do that? Why do we need that? Because as we argued earlier that we need a length scale and a velocity scale, okay, U0 and L0, okay, and the best velocity scale that you have is a square root of kinetic energy, right, which is basically nothing but a square root of half u prime plus b prime and w prime, right. Remember, in RANS we are not resolving u prime, he prime and w prime separately, okay, but we are looking for statistical parameter. For example, in the RANS you will never get what is your u prime, what is your v prime, okay. Why? Because you are only solving for the mean flow, okay, and then in those cases u prime equal to 0, v prime equal to 0, w prime equal to 0, okay, all these quantities are 0, right. So, we do not get this, but what we do get from the RANS flows is basically u prime v prime bar, okay, this is the stresses, or your u prime is I mean square plus v prime square plus w prime square and so on and so forth, right. and how do you get that? Is basically you know the eddy viscosity and you relate it to the mean flow gradient and you can calculate all these parameters. So, you know you can get the turbulence kinetic energy, you can get the stresses, but not the individual fluctuations. If you are doing LES or DNS, you do not solve the mean flow equation, but you solve the exact equation, exact Navier-Stokes equation. In those cases, you got the get fluctuations. Of course, in those cases also, if you take the mean of those fluctuations, you are going to get 0, right, because that is the property of the flow, right. So, we want to derive the K transport equation. Okay. So, the K transport equation is derived exactly from the first principle. Okay. You can derive it from first principle, unlike the other variable which is like maybe epsilon or omega, which cannot be derived from the first principle. Okay. So, how to derive this K transport equation? So, we have derived this instantaneous, this is the instantaneous flow equation, which is basically your Navier-Stokes equation, momentum equation, let us say. Okay. And what we did, we used the Fabry averaging or Reynolds averaging, and we got this mean flow equation. Okay. Up to this one, there is no problem, and because of averaging property, we got another stress, which is the Reynolds stress for the incompressible flow or Fabry stress for the compressible flow, okay, depending on how you are doing the averaging. Now, we want a equation for the fluctuations, right. So, what we can do, if this is my 1, okay, and this is my 2, so I do 1 minus 2. So, if you do 1 minus 2, this is my du by dt, this is ui bar by dt. So, this is partial t u minus ui bar, right, which is nothing but partial t ui prime, right. So, we will get an equation in terms of ui prime. So, the first term this will become ui prime if you subtract, okay. In the second term, if you subtract this from this, because this is a quadratic quantity, you will get two quantities here, okay. The mean multiplying with the derivative of the fluctuation, and the fluctuation multiplying with the derivative of the mean, right. So, these are the two quantities that you will get when you subtract this term to this term, okay, the convective term, okay. Okay, so yeah, there will be actually a third term also, which is basically multiplying the fluctuation with the derivative of the fluctuation, okay. Here if you see, this is p minus p bar, this is very simple, this will become p prime. Here if you see, if you just take the first term, okay, ui minus ui bar, so that will give ui prime, and this is negative, which is in the mean, it will become positive in the fluctuation, okay. So, the mean is basically getting the energy, the minus rho prime u prime p prime bar is positive, so it is getting energy from the flow, and basically fluctuation is kind of dissipating it, okay. So, in order to get the K transport equation, so what is K? K is basically u prime plus v prime plus w prime by 2, right, okay, or you can write it as ui prime bar by 2, right. So, you already got the equation for ui prime, okay. You multiply it by ui prime again. So, you can take this equation and multiply the entire thing by ui prime, right, the entire thing by ui prime. So, this will become ui prime. So, this will become ui prime del ui prime by del t, that will become del by del t half ui prime, okay, that is nothing but, I mean you can take the average there, that will become del by del t of k, okay, provided, I mean this is when you say ui prime, you are actually summing over all the u prime, v prime and w prime, right. So, you will get the equation for the turbulence kinetic energy, this is what we have, right. So, this is the temporal term, okay, and we look at different terms here, okay, these are basically the production terms, okay, these are the diffusion terms, and this is the dissipation term, okay. So, let us look at all these terms separately, okay. So, K represents the kinetic energy, Pk represents the production of the kinetic energy, which is happening from the mean flow as well as from the fluctuations, okay. And then we have this production of diffusion of this kinetic energy due to the pressure, due to the viscosity, due to the transport, okay, and as well as you have the dissipation, okay. So, this is a very important term, okay. Let us look at this in the next slide, okay. So, this is the production of K by the mean flow gradients, okay. So, this term is the production term by the mean flow gradient, Okay, these two you can take it together, that will give you the total derivative here. Okay. And then you have diffusion of kinetic energy, turbulence kinetic energy by the pressure, okay, by this viscosity and by the Reynolds stress, right. And finally, you have the dissipation of kinetic energy by viscosity. Okay. So, this is a very important term, this is how what indicates how the kinetic energy is getting dissipated, right. So, if you look at this unit, okay, so this is meter square per second, okay, and this is meter per second by meter. So, this is 1 by second, this is also 1 by second. So, this is meter square per second cube, right. So, this is the dissipation of kinetic energy by the viscosity. Okay. Now, for the compressible you can write it in a slightly different way. Okay. So, I am just giving you overall picture. So, this is your temporal part, then you have the advection part which is then incompressible as well compressible, then you have this diffusion part, okay, and the diffusion part, this entire thing, okay, you have some assumptions here that you basically ignore some of the terms here, especially some of the models which they ignore this diffusion due to the pressure, okay, and you basically mostly take this diffusion due to the viscosity as well as the turbulent transport, okay, and this will be giving you mu t. So, this is mu del grad k, which is this term, okay, and this is your basically the diffusion due to Reynolds stress. So, which is given by mu t by sigma k, okay, by sigma k is basically nothing but a constant, okay, which will be is an empirical constant which can be basically evaluated using different comparing with the different experimental data or even the DNS data. And finally, we have terms. So, this is the production of the kinetic energy, okay. So, this term, this production of the kinetic energy, okay, and then you have dissipation, that is why the sign is negative, dissipation of the kinetic energy, and if there is any source or sink, then you can put everything together here, right. So, basically you have you can divide the kinetic energy equation into 4 parts, the rate of change of turbulence kinetic energy, how it is getting advected, okay, how it is getting diffused and how it is being produced and dissipated, right. Now, you need another equation, right. The kinetic energy equation can give you only the velocity scale, right. You also need another scale for your length, right. Now, different models use different dynamical equations for them, right. So, because you are talking about the epsilon model, I am going to talk about the epsilon transport equation. So, epsilon is nothing but as we saw earlier, nu del u prime by del x j del u prime by del x j. Okay. This is basically how the kinetic energy is getting dissipated, right. So, it is a dissipation rate. Okay. So, we want to find out a equation for this. Unfortunately, you cannot derive this equation from the first principle. Okay. You have to basically use some kind of argument that we have seen in the turbulence kinetic energy. We have seen the temporal term, we have seen the advection term, the diffusion term and the sources and sink term. Okay. So, because we cannot derive from the first principle, we will follow the same pattern as we had the turbulence kinetic energy. Okay. So, we will have the temporal terms, we will replace the k with the epsilon. Okay. We have the advection term, replace the k with the epsilon. Okay. And then we will use a different coefficient here, sigma epsilon. Okay. And this is your diffusion of the dissipation rate. Okay. And then there will be like you will basically change it this pk epsilon. So, we had this pk earlier in the kinetic energy, we will multiply with the epsilon and divide by k, and then we will use another constant which is c epsilon 1. Okay. Again this epsilon transport equation is heavily modeled. Okay. This is not derived from the first principle. Okay. So, you can see many different transport equations for epsilon in different models. If you are going for standard K epsilon or the RNG K epsilon or I mean any other K epsilon like Razor K epsilon, this equation will be different. Okay. And the coefficients also like the c epsilon 1, c epsilon 2, they will be different, right. So, this is these are basically sources and sinks for the epsilon transport equation. Okay, so now we have the K transport equation and epsilon transport equation. We can derive the velocity scale and the length scale from this, and from that we can find the eddy viscosity. So, how do we do that? Let us see that in the next class. Thank you very much.